record this for the benefit of our TOEFLers. Hello, TOEFL people. Test of English is a foreign language. Sometimes I think all my students should take it.
I've got good or correct.
It's not about
Gooder than I. Okay. So, in your notes, I'd like for you to review this a little bit. What is, don't say it out loud, just write it in your notes, the derivative of sine x. The derivative of cosine x. And the derivative of tangent x. Go, go, go. Just write it. Give me the result. Okay, Yun, derivative of sine x is? No. Cosine x. Derivative of cosine x is, Christian. Yep. The derivative of tangent x, yes sir.
Secant squared.
Yes. Now, how many of you had forgotten this one? Oh, come on, be honest. How many of you had forgotten it? Not a couple of you. No shame in it, because everybody's going to forget it at some point in their lives. So if I forget it, Suah, how do I remember it? What can I do to get it? No. Math is not about memorizing random theorems. Math is about seeing how it all connects. How do I get it to connect?
You prove it like a pro.
And I prove it, not like a product, but like a... What is tangent? Sine over cosine. That's exactly right. At this time, I'd like for all of you to supply the details. Get me from here to here by rewriting tangent as sine over cosine and using the quotient rule. Go.
Are you telling me or doing?
I don't care. You don't need any trigonometry.
I don't know it like.
Cease with the excuses. Get the paper out. Do it.
What's up, Jazz?
Sorry.
The quotient rule sign, I did not make it up actually. I learned it from somebody else. I did make up the quadratic formula song. And the distance formula Gregorian chant. I didn't have you guys do that one. X1 minus X2 squared plus Y1 minus Y2 squared. All of this is distance squared. Amen. I didn't see it for all distance. That's okay. Okay, Suah, tell me the details. Nice and loud.
cosine 8 over 3x sine x
Uh-huh. Squared. Yeah, there you go. And we usually write that as cosine squared x. But it means, as she has said, the cosine of x squared. Keep going, Suah.
See, it's right there.
Well, you have to keep going in real time. Students will often get themselves befuddled, that's not an English word, because they try to do the whole thing. Am I right? Are you looking at this whole thing and going, I have no idea? Yes. Don't. Instead, focus on each individual piece, because each individual piece is actually something that you can deal with. All of these things that we already have right here, we don't need to change. The cosine x is still the cosine x, and the minus sine x is still the minus sine x, and the cosine squared x is still the cosine squared x. The only two pieces you need to focus on at this point are just the calculus pieces. What is the derivative of sine x? Of course. Yes. See, I didn't need to figure out the whole thing to figure out that small little piece. That's how mathematicians think. They focus in on small little pieces to actually deal with, because the result is guaranteed here. The derivative of sine x is cosine x, no matter what's happening in the rest of the problem. You see what I'm saying? All right, how about the derivative of cosine x? See? Easy peasy. Good. Keep going. Now we can start simplifying a little bit. Good. Very good, very good. Keep going. Now she needs a little bit of insight. This is the only point in the process where knowing something helps. Knowing something tricky helps. Hey, there we go. Because of the, what's our term for this identity? What specific one then? Whose theorem gave us this? Pythagorean identity. That's it. Good. And now, carry it home. 1 over cosine squared x is the same as, and we're done. That's a good job. Everybody give her a hand. And all of you should be capable of doing this zippy quick. Which means if you're going to do it zippy quick, you're going to have to practice. And if you're going to practice, you're going to need to have a little time to practice, and what better time than sitting bored in those classes, right? Just kidding. Good.
I did it the 1 plus tan squared way.
That's fine. Anything that's valid, math. All right, so we have 2 goals for today. The first is that I want to observe a pattern in the derivatives of sine and cosine and see if we can pursue that pattern. And the second is that I want to get the derivatives of our other 3 trig functions. And if we can accomplish those 2 things, we're happy. It's been a good day. So let's talk about patterns. I would like for all of you to give me, you've already done this, but again, the derivative of sine x. And then after that, I want you to give me the second derivative of sine x. And then after that, the third, and the fourth, and so on, and stop when you come back to sine x. Go. Stop when you start repeating yourself. Earl, what you got?
Cosine x. Negative sine x.
Uh-huh.
Negative cosine x.
Uh-huh. And the fourth derivative is sine x. And that brings us back to dou. You all watch Sound of Music at Christmas time, right? You know what I'm talking about?
Not a question.
Yep. So, what does this mean for us? Well, this means something very interesting. It means that if I were to continue on, what would the fifth derivative be? Cosine, the sixth derivative, seventh derivative, eighth derivative, sine, and so on. What's that? Ooh, that is a profound observation. There's a lot more to that than you realize. Like what? What did you say? It's like the powers of I. I, negative 1, negative I, 1, I, negative 1, I, negative 1, negative I. Good catch. Okay. So this suggests to us then that we might very well be able to use this pattern to solve seemingly hard problems. For example, what is the 795th derivative of sine x? Well, I can tell you the wrong way to do this problem. That's exactly right. But what if I could take and leverage my pattern right here by observing that my pattern has a length of how many? 4. That's exactly right. Which means that I'm going to repeat my pattern in cycles of 4, so that if I can write 795 as a multiple of 4 plus remainder, then I would know where I am in the pattern. Everybody do that. Write 795 as 4 times something plus remainder. He reaches for his calculator. Bad form. Bad form.
Well, if it was 3 years ago, it's
Right now you could have done it. Skip ahead to 800. 800 is 4 times what?
200.
Now go backwards to 795.
well, it's,
197.
Plus 3. That's exactly right. We can throw these cycles away. We don't actually care about the 198 part of it. We only care about the fact that the 795th derivative should be exactly the same as the third derivative. Boom. Negative cosine x. And we are done. What is the 1000th derivative of sine x? Sine x. Boom. Done. What is the 522nd derivative of sine x? That's right, so it's equal to 0 3.
Oh,
Yeah, so what's the 522nd derivative of sine x? 522nd, 522.
negative sine
It's
x.
going to be negative sine x. That's right. You're just dividing by 4, taking the remainder, and that's it.
Why would
See
you
it?
need to know the millionth derivative of sine x?
You don't know yet, but you might.
because if Robert came up.
In a how-to class in your future.
Tell me, what is the 900 derivative of sine x? I'm gonna
Good.
So much for pattern matching here, but I want you to observe how we dealt with the patterns. We found the length of the cycle, and then we used division with remainder to determine where we were in the cycle. That's it. That's it. All right. The derivative of cotangent x. I'll bet you know how to do this. Make it happen. Go.
I don't know. One over 10.
You could do it as 1 over 10, actually. But 1 over 10 is the hard way. The easy way is cosine over sine. bless you.
I'll do pretty good, cosecant.
See. Just because I was in a little bit of a hurry, I omitted the DDX portion of the process there and got straight to this. Did all of you get so far? And now we have a very thinly disguised Pythagorean identity going on here. How does that top simplify? -1, that's right. So that when the dust settles, what I get is negative cosecant squared, which is really nice because it reminds me of the derivative of tangent, except that instead of secant squared, it is the negative cofunction. How are we doing? Does this make sense? All right, this leaves us only with secant and cosecant. And actually, those are equally easy. We're just going to end up with a slightly different form here. I'll bet you know where I'm going. How am I going to rewrite this? 1 over cosine. I will not use the limit definition if I do not have to. Thank you very much, Josh Butler. The limit definition is really, honestly, the last resort because it's such a pain in the neck to do, right? I can, but I don't want it. I would much rather use my derivative rules if I can. That's the point of theorems, is they give you shorter bits of reasoning to your final solution. Okay. So low d high, less high d low. Long line down below. The denominator square will go. Let's kind of turn into a, sounds like a jumper line almost. Denominator.
Even though it's 1 over cosine, the denominator is just cosine x, or would it be 1 over cosine?
So the denominator is the bottom fraction. The numerator is the top. Okay. This is interesting. What is the derivative of 1 exactly? 0. So this whole term, by, exactly. And what is the derivative of cosine x?
Negative sine.
Times a -1? Cosine x. And so I get this result here, which is not nearly as elegant as the previous result. This is a perfectly good answer. However, all of the cool mathematicians rewrite it. Because when I rewrite it, I can turn it into not a fraction. By writing this as 1 over cosine times sine over cosine. Everybody take a quick look here and make sure that the algebra checks out. Which is the same then as the first factor is secant x, and the second factor is tan x. Secant x tan x is the derivative of secant. That's kind of a strange derivative, isn't it? You might have discovered that on yesterday's homework. Yep.
Oh, yes, sir.
Well, our last one is going to be cosecant, and you know already how this is going to go. We're going to rewrite in terms of 1 over sine x and use the quotient rule. Definitely not the limit definition, Mr. Butler. Other Mr. Butler. just like so. And once again, in the top, the first term, goodbye. And the second term, -1 times the derivative of sine x is? -1 times the derivative of sine x is negative cosine x, that's right. All over sine squared x. And once again, we're going to rewrite as -1 over sine x times cosine x over sine x. Mr. Butler, the other Mr. Butler, tell me what -1 over sine x could be written as.
Negative, one of those cosecant, yes, cosecant.
Cosine. Okay. And cosine over sine? That is. And so we now have a complete set of derivative rules for our 6 trig functions, and it wasn't too terribly painful. Yes, sir.
Can we not just keep it as negative cosine over sine and then make the other one 1 over sine? Or would it have to be negative 1 factor?
Well, cosecant x times negative cotangent x is the same as negative.
So it could work either
So
way.
the factor can work either way. Our custom is to pull coefficients to the outside. Well, let's take and generate a chart here, because we are going to have many of our 6 trig derivatives frequently. Hated when that happens. If we call these 3 our big free trig functions, then the derivatives of the big free trig functions are like so. And the derivatives of their cofunctions are the negative cofunctions of each of the derivatives. Take a look. What? So that in terms of remembering, I only need to really remember 4 facts, 1, 2, 3, and the fact that each of the derivatives of my cofunctions is the negative cofunction of the derivative of the original. If I've got that, then I've got it. But, Suha and others, should I learn this by trying to cram it into my memory cells? No, it will not stick. You'll be sitting there banging your head against the wall during some test. But what was that derivative? I can't remember. Should I learn them by proving them to myself? Yes, that's how we get things to stick in memory, is we make connections with what we already know, so that it all sticks together. When should I prove them to myself? When I have opportunity. It takes about 5 minutes or less to do each one, and that's it. So you have a great weekend. I'll